Okay, so we're starting 8.2 today, and we're going to investigate the connection between the Cartesian and the polar graph world. Okay, so just grab a piece of graph paper there, and we're going to start with the simplest function I can think of, and that's just r equals theta. R equals theta. This reminds me of the good old equation y equals x. It reminds me of y equals x. So I'm going to try to make predictions of what r equals theta looks like based on my understanding of y equals x. Okay, anytime you learn something new in life, you're supposed to connect it to what you used to know. That's what understanding is. Understanding is, in theory, this is what people believe understanding is. It's when you can take a new idea and connect it to your old ideas, and when you can do that, you understand it. If all you ever do is get new ideas and you pile them onto the old ideas, but you have no connections, you don't understand it, you just know it. There's a big difference. So if you want to understand, connect your new idea to your old idea, and then it'll deepen your depth of knowledge. Okay? All right. It's kind of like the difference between wisdom and knowledge, right? So let's just start with the idea of y equals x. What do you know about y equals x? It's a line, right? Slope is 1. What is its behavior? As the x gets bigger, what happens? The y gets bigger. Right. Okay? Now, last period, I wrote this on the board, and one of the students shouted out, "It's a spiral." It's a spiral. Actually, they whispered it. I think they're too embarrassed to say it loud. They knew instantly this was the graph of a spiral. You can probably guess who it was. How did they know that? Well, what does a spiral look like? Show me with your hands. What's a spiral look like? So spiral is a circle that starts small and then grows in its radius, right? So this is a graph where as x gets bigger, y gets bigger. This is a graph where if what? Theta gets bigger, then r gets bigger. You see. So this student obviously was 2 steps ahead of us intellectually right now, maybe, but what he's saying, don't look at the calculator graph. Don't look at the calculator graph. You can spoil your understanding. Your predictions first, test them there, right? So we're going to understand that as we choose rays that are larger and larger, like this, the points are going to get further and further from the pole. R will grow when theta grows. And it's a 1-to-1 growth. So for example, if you just pick theta equals 0, r is theta. So what is r? 0. Correct. So you can make a table if it helps your mind. Usually we put the theta column first. If theta is 0, then r is 0. That means if we're on the first ray, we start where? Right at the 0th circle. In other words, the pole. Good. On the other hand, if theta is pi over 6, which I believe is your first, on your graph paper, that's the very first bold ray. So find the first bold ray on your graph paper. That's pi over 6. When theta is pi over 6, then r is pi over 6. Which ring is that? Well, it's 3.14 divided by 6, roughly. About a half. In other words, when we reach the ray pi over 6, we are out here at about halfway into the first ring. Now your graph paper is very small, so if you want to, you can make every ring 0.5. Okay? In fact, I'll do the same so you guys can follow my notes a little better. So I'm going to call this first ring 0.5. So this will be ring 1 out here, and this will be ring 2. I think yours is going to go all the way to ring 5, even if you do a double count like that. So why don't you guys label your rings 1, 2, 3, 4, 5. Okay? So the second ring is ring 1. The 4th ring is ring 2. The 6th ring is ring 3. The 8th ring is ring 4. And the last ring, the borders of your paper, is ring 5. this should say 0.5th circle. Okay, let's go on and look at our next ray. On your graph paper, I believe your next bold ray is the pi over 6 ray. Okay. So find the next bold ray on there. What am I saying? Pi over 3. 60 degrees is pi over 3. Thank you. So pi over 3 as a decimal is what? What's 3.14 divided by 3? About 1, right? So what does that mean? When you plot on this bold ray pi over 3, you're out at approximately 1. .14 divided by 3 is about 1. Okay? Next is pi over 2. That's straight up on the graph paper. Right? And of course, pi over 2 is 3.14 divided by 2, which is close to 1.6. It's 1.57, blah, blah, blah. So now we're out at approximately the third ring. Remember, each ring is about 0.5. So now we're out here, 1.57. And you can see that what's going on, especially if you connect these, the larger your theta is, the larger your r is. In other words, your graph is growing radially. So no wonder the student said it's a spiral. Right? So first we try to understand it. Now we grab our calculator and we just watch it grow. Okay? So let's play around with the calculator now. This is the fun part. Get your calculator out. Make sure you put it in polar mode, if it isn't already. Make sure it's in radians for some of our later problems. And go under r equals. Let's clear out this old function and put in just simply theta. Is anyone having trouble finding polar mode? It's crucial for your understanding this period. Does anyone have a Casio?
Yeah, I know.
You have the HP, right? Are you able to find polar mode?
Yes.
You're good? Okay, pretty important. So you'll notice when you press window, okay, you can press graph if you want, but let's all press window too. Let's all get into this screen. If you do a zoom standard, you need to know this, your calculator will always default back to these settings. So even if your objective was just to sort of rezoom and you press zoom standard, it's going to default everything back to this. So let's talk about these numbers, okay? 0 means 0 radians. 6.28, does anyone recognize that number? That's 2 pi. So what's going on is the calculator plans on drawing exactly one of these green loops. 1. If you want more loops drawn, you need to change the theta max. So I would like to see 25 loops of this amazing spiral. So I'm going to put in 50 pi here. That's going to be 25 beautiful loops of my spiral. Each loop is 2 pi. Okay? The theta step, keep it under 1.0, or actually keep it around 0.1 and you're good. Okay? What it's doing is it's trying to graph as many points as possible. So the smaller you make this number, the more fine scale your graph looks and the more beautiful it looks. So I don't recommend changing your theta scale. I think you should just keep it at 0.1 at all times. Technically that's pi over 24. I figured it out earlier. So it's graphing every 7.5 degrees, it'll plot a point. And it will graph so many points, it's going to look real beautiful. If you want to make it even smaller, your graphs will be even more pretty. But there is a limit to how many points it can draw on these horribly pixelated screens. If you have the TI Aspire, or one of the, like TI-89 that has a really fine-scaled screen, you can make this much smaller and get better, it's like megapixels, you know, more smooth graphs and better look. On the other hand, it slows down your calculator and wastes your battery. So, kind of find that balance point at about 0.1. Okay? So now the rest of these settings in here are your window size. So right now it's set, you can see, to show you the negative 10 on the x-axis and 10 on the positive x-axis, and between negative 10 and positive 10 on the y-axis, you see those are normal zoom settings. Okay, now it's time to press graph. We're going to see probably not all 50 loops. It looks like it only made it around a few times. But if I zoom out, I'll get to see potentially up to 50 loops. Now my calculator is still thinking right now, so I would like it to stop thinking. And so I'm going to press on, which will stop the processor and allow me to do my zoom out. So if I press zoom out, on some calculators you have to press enter after you press zoom out. I get to see a little more. I'd like to zoom out again, actually. It's still thinking. Let's press on to stop that processor. Still thinking. I'm going to zoom just out several times. Okay, if it doesn't seem to be working too well on the zoom out, what you can do is just go under window and just change these yourself. So just change this to like negative 100, positive 100. Same thing with the Y min, Y max. Negative 100, positive 100. And then you'll get to see more. See, I was hoping to see 25 spirals there. Now, if they don't look like perfect circles, it's because the rectangular piece of plastic that they used when they made the calculator was not a square piece of plastic. So this piece of fake glass is not a square. And it's showing you negative 10 here and negative 10. Negative 10 and 10 on the left and right, and negative 10 and 10 on the up and down, but it's physically wider for this negative 10 and 10. So you can fix that by pressing zoom square. Zoom square will fix that issue. And it will not have a distorted graph, it will truly look circular. So now those look a little more perfect circle, you know? You can see it's still a little bit pixelated looking. If you want to improve that, you have to decrease your theta step, make it like 0.05 or something. But I think this is the TI-84, so I don't think you can even handle high resolution. But that's pretty cool looking. Does that thing pass the vertical line test?
Not even close.
Not even close. It fails it an infinite number of times. It's terrible. Which probably means, listen, if I try to convert this equation into y's and x's, I'm pretty sure I won't be able to isolate y. Watch. Now we're going to try to isolate, we're going to try to convert it, okay? This is one of the skills. So everybody do this with me. You're going to change this to square root of x squared plus y squared. And you're going to change this to inverse tan of y over x. Problem is, you're never going to be able to get y by itself. Tangent is an infinite valued function or multi-valued function, which means if you tan both sides, you're going to have y buried inside and outside, and there's an infinite number of y's here. And if you try to separate it into like y1 equals and y2 equals, there's an infinite number of them. Okay, so that's not happening. We're done with this problem. I am not going to isolate y. I don't even know how. Aside from approximation. Just throw the calculator wherever. Okay, any questions on that? Okay, so what did we learn from that problem? We learned a couple things. We learned that just as x and y grow together on this graph, so r and theta grow together on this graph. Okay, now let's go back to the idea of y equals 1 over x. I'm sorry, y equals x. And think with me here. So everybody put the calculator down for just a second. Everybody? One of the things we did with y equals x is we would put like a 1/2 in front of it. Right? And what does that do to the graph of y equals x when you slap a 1/2 on it like that? It's some kind of a stretching effect. It is a horizontal stretch by 2. It's also a vertical compression by 2. Right? In other words, it changes your slope. Isn't that true? Okay, don't graph it on the screen, but what would happen if we did r equals 1/2 theta? Just use your common sense. Okay? So by putting the r equal to half theta, this column in the table is not going to change. But all of these will be half of what they were before. See? R's will all be half of theta. So what happens to all my green points? They are at half distance. You see? Can you visualize it? So they're no longer out at 0.5 and 1 and 1.6. They're at half of that. Can you sketch it? Try it. So if this is r equals theta, what would r equals half theta look like? So you're learning this, okay? This is our shrinking in the world of radial. We're shrinking in the radial sense. Okay, so if you divide all of these by 2, obviously the first point does not move. Right? But the point that was out at 0.5 is now only at 0.25, you see? And the point that was out at 1 is only out at 0.5, and the point that was at 1.5 is now at 0.75. And basically the whole spiral shrinks. Now, is this a vertical compression or a horizontal compression? It's really neither. It's a radial compression. That means everything's coming in towards the pole, half. Right? So just like this is getting closer and closer to x equals 0 and y equals 0, right? When you do that, you're dropping the y down to 0. So you're bringing the circle in towards r equals 0. You're crushing it this way. Okay? And if you did 1/3 or 1/10, it would be even tighter in its pitch. The spiral would tighten. And if you put in a 5 here, right there, the same way this would steepen and the y's would get bigger, so this circle would grow and the r's would get larger, you see. So now let's see, what would r equals 2 theta look like? What would that look like? Radial stretch, yes. So r equals 2 theta would be, everything's doubled, see? First point wouldn't change, but everything would double its distance, and it would very quickly outgrow your paper. So this is just so much better than me saying, r equals theta is a spiral. Memorize it. And it grows if you put a bigger number in front of it. This way you're at least connecting the ideas from before to the ideas now. So what do you think we should call this shape? Because some of these have names. Spiral. Can we call it the spiral of pre-calc 2014?
Yeah, the Archimedes spiral.
Unfortunately, it has a name. It is Archimedes spiral. He got to it first. So we'll have to give him the credit on this one. This one is called, write it down, r equals a theta is the spiral of Archimedes, except I can't spell. Spiral of Archimedes. Okay? And obviously if A is bigger, the pitch grows on that spiral, the separation between them. Okay, you'll notice something interesting about the graphing calculator. There's one more thing we need to talk about before we leave this problem. Watch. If I make it 3 theta, we said it would grow in its pitch. In other words, the spiral is not as tight as it used to be. We understand that as radial growth now. But you'll notice something about the gaps between the spirals. They're all perfectly even. You see that? What do you think that corresponds to in the world of, what I just graphed was r equals 3 theta. 25 loops of it, I'm pretty zoomed out right now. What do you think this has anything to do with y equals 3x? And I'm not talking about the fact that it's bigger than y equals theta, or r equals theta. I'm asking, why are these gaps all the same? Okay, what's growing at the same rate?
R and theta.
No.
Finish your sentence, because you said it's growing at the same rate. It's a bad word in math. You have to say what's growing. The spaces are caused by the circles. R is growing at a constant rate. Okay. And in the graph of y equals 3x, what's growing at a constant rate?
Y.
The y's are growing at a constant rate. That's why it's a straight line, right? So this is very interesting. The straightness of this manifests itself in the even spacing of the circles here, isn't it? Because if this was growing in its steepness, like gravel, that would show up as increased gaps as the radius grows faster and faster. So there's so much you can learn from one simple example. The spacing here corresponds to the straightness here. Raise your hand if you follow that argument. So y is increasing at a constant rate. The circles are growing at a constant rate. A lot to learn. Yes?
Well, it looks like R is equal to theta squared plus 2 theta plus 1.
That's a great question. So what you would have there is definite radial growth. Every time you plug in a bigger theta, you get a bigger circle, right? And it's very drastic. Even a slight change in theta there, since you're squaring it, would increase the amount of radius by a lot. So let's take his idea and play with that. He's wondering what happens when you square the theta. I believe it will grow really fast. And I don't think it's going to have a constant pitch like that. Like that gap is going to not be so consistent. Okay, so let's say you did 3 theta squared. Notice it grows faster and faster. In fact, it grows so fast it's off the screen. So I would need to radially compress it to see it. That's not hard to do. I'll just slap a 1 over 1,000 in front of it. I'm just going to divide this by 1,000 to radially compress it so we can see it better. Okay, so here come the circles. They're pretty small at first. Maybe 1,000 was too much compression, Mr. Shore. Here it comes. They're very tight at first, but because theta is squared, just as y equals x squared grows in its steepness, so the gap is widening between the consecutive circles. Kind of wish I had not used a 1,000 radial compression. It was just a little drastic. What do you have there, 100?
Yeah.
Let's try 100. As long as you're understanding it, we can do 2 examples today. The rest is just memorizing names of cool shapes and stuff. I would like to get to the rows if we can. Yeah, there you go. So you can see a slight increase. The gap is increasing here. So if this gap is 1, the next time it's 1.3, and so forth. And that's because of the curved nature of y equals x squared. If you want it to be even more drastic, then you could do like x cubed, which is even steeper. Okay, can you think of a graph? So let's just summarize so far. R equals 3 theta is a spiral with constant pitch, right? Like that. And then 3 theta squared has a growing pitch, right? And that's because y equals 3x squared actually has a steepening effect. It gets steeper and steeper. Can you think of a graph that gets shallower and shallower as you go out? Can you think of a graph that does something like that? Rad x, okay. So we could try like rad theta. Or ln theta. Ln looks kind of like this. Those would be fun to play around with. Let's graph rad theta. I think what's going to happen is it's going to start out by growing quickly, and then the pitch is going to get smaller and smaller. So that's interesting. Let's try that one. I'm going to do rad theta. Last period I did ln theta. So rad theta means just as this grows at first quickly and then sort of flattens, so the circles will grow quickly and then sort of slow down in their growth. I think I need to do a zoom standard, which means I'm only going to get one loop-de-doo. Remember it resets back to one loop? So I'm going to press window and make sure I get a good 5 loops in. That means I'm going to put in a 10 pi here. So I did a zoom standard and changed my theta max to 10 pi. Yeah, look at that. The circles are getting tighter on themselves as we go out, see? In other words, the gap between the circles is shrinking. And how does that manifest here? What's happening to y as x gets bigger? It's growing less. It's growing less than last time. In the same way, our circles are growing less as time goes on. You understand? Okay, so there's so much to learn. And we haven't even left the first example. Okay. So now I have a question. If putting a number in front of the theta makes it grow, and putting a fraction in front of the theta makes it shrink, and putting a square root on the theta makes it grow but slower, and putting a square on the theta makes it grow and grow faster, what would happen if, and do not graph it until you've thought about it, what would happen if you put a sign on our theta? There's so much to learn here, okay? This is like gold. Do not graph it on the screen, okay? We want to think about it first. So let me clear my ink, okay? And let's think about what we know about sine. You guys have studied the sine wave so much. You understand sine, right? You know the domain, you know the range, you know the roots, the x-intercepts, right? We're going to try to understand r equals sine theta from y equals sine x. So y equals sine x starts out by doing what? It starts by what? Growing or going down? It starts by growing. We can expect our graph to do the same. It then slows down in its growth and ultimately stops growing and then comes back down. So it shrinks. The circles will shrink. So we're expecting our circle to grow and then shrink in the same way this rose and fell. Interesting. This will happen in the first pi radians. We would expect in the first half term for the object to grow and then shrink. Shrink back to y equals what? It's going to start with a y of 0, grow to a y of 1, shrink back to a y of 0. Now think radially. It will start with an r of 0, it will grow to an r of 1, and then it will shrink to an r of 0. And this will all happen smoothly and within the first pi. Can you picture it? So let's just analyze that real quick. What's the highest that sine can ever reach? 1. So when we graph r equals sine theta, what's the biggest the radius will ever be? 1. When does it achieve this? At half pi. On which of these rays will our graph grow to its furthest from the pole? On the pi over 2 one, right? So here's what I'm expecting. I expect it to grow. I expect it to grow no bigger than 1. I expect it to shrink. And I expect it to return to 0 before it reaches pi. Follow it? In the same way that this rose and fell between 0 and pi, I believe that this will grow and shrink before it reaches pi. So the radius is growing out, reaching 1, growing back down. If you want to watch the points move, they would look something like this. They will reach their maximum at the top and then collapse back in like that. I can easily verify this on the calculator. What would happen if you put a 2 in front of your sine? What would happen to the sine wave? The old school graph right here. What happens to it?
It gets on period
No,
level.
no. This is a vertical transformation. I'm multiplying by 2. What happens physically to the graph? It gets taller, yes. The y's double, correct? So what happens then to the r's if I put a 2 here? They double. What happens to my little circular diagram when I put the 2 there? What's the biggest that 2 sine theta could ever reach? 2.0. That's right. So you understand range. In other words, it'll still grow and shrink back in before pi, but it will do so and reach a radius of 2 at most. And it happens at pi over 2 because the only difference between y equals sine x and y equals 2 sine x is the height of the graph. In other words, the radius is larger, but nothing about theta has changed at all. Or you could say each of these red points will double their distance along their respective ray and produce a larger circle. Now, is it truly a circle? Do we believe it's truly circular, or is this just a loop of sorts? Like, is it truly a circle? Well, this is where taking r equals sine theta and converting it to rectangular coordinates will 100% convince us that this green thing, which I'm now highlighting in bold blue, is truly a circle. It really is a circle. Watch this. So let's go back to just regular sine theta. I believe it's a circle. Here we're going to prove it. What am I going to do with that r? I guess I could replace it with like root x squared plus y squared, but I might have some trouble with the right side. What might I want to multiply both sides by? Yeah, if I multiply by r here and here, you saw this is one of my big tricks in the video. The left side is now r squared, also known as this. And the right side is simply y. You can take it even further, but this is definitely a circle. You can bring everything to one side like this. Should be a minus here. You could complete the square like you did in your Algebra 2 class. What's half of 1? Half. Square that. 1/4. You could add a 1/4 here and add a 1/4 here. And this factors beautifully into x squared plus y minus a half squared equals 1/4. A radius, 1/2 circle, that's the square root of this number, centered at 0, half, 0, half. It is this circle. It is centered at 0, half. It has radius half, and that's proof enough for me. So this is when I get excited and I see, oh man, that really is a circle. And I could have done that before doing any plotting, right? I could have just converted to Cartesian, recognized the equation, that's a circle, sketched it, and totally ignored the radial world. What I would have missed out on is the understanding of the radius growing to 2, and then growing out to 1, and then collapsing back to 0 in the first pi. So this brings up one last question for me. What's going on between pi and 2 pi? Because I never even got that far. What happens is the circle just retraces itself. So if you graph this from 0 to pi, you get the full circle. If you graph it from 0 to 2 pi, it just draws the same circle twice. Tomorrow we'll see what happens when you put a number on the inside, like sine 2 theta, sine 3 theta, sine 5 theta. We're going to get some really cool pictures starting tomorrow. Okay, but that's day 1.